The problem of variance of first passage percolation is an enduring mystery, and since the linear bounds of Keston and Kalai, the famous result by Benjamini, Kalai and Schramm of that gets a logarithmic improvement, and then it's been generalized, but not really improved until now. So very excited to hear the next talk by Allan Sly from Princeton about this topic.
Oh, thanks. Thanks for the introduction, Yuval. So this is a mix of some newer and older results, and the older ones have been taking an embarrassingly long time to write up. But the first part is on the archive, and the second part will be in the next couple of months. So I'm going to talk about first passage percolation, which is sort of finding shortest distances in a random environment. So you imagine that a crazy town planner comes and erases all the speed signs and puts a different random speed limit on every block. And then you go to Google Maps, or maybe here you can't go to Google Maps and you go to Baidu Maps, and you find the shortest path in this random environment from A to B. And we want to understand how that, how the randomness affects that. So the sort of math model of that is we'll have a random weight on each edge of the graph that there'll be IID. And we'll think of this as the time it takes to cross that edge. And then the passage time between A and B will be the minimum over all paths between A and B of the sum of the weights along the path. And so we'll think of this as how long it takes to get from A to B. And we'll talk about the associated growth process, BT, which is the sort of what you can reach from the origin within time t. Okay, and because we're doing probability, we'll be interested in sort of large random systems, and in particular how distances or these passage times grow as n tends, as the distance grows. And so there's a law of large numbers. It does take quite a while for things to come up when I should. By Kingman's subadditive ergodic theorem. So the passage times are subadditive, going from A to B and then B to C takes at least as long as the best path from A to C. So if we go in some direction, the passage time in sort of length n in that direction divided by n will converge almost surely to some constant mu that depends on the direction. And so it's not the same in every direction. Going in the direction of the axes will in general be different from going in, say, the direction of the diagonal. Partly because, say, there's more paths in the direction of the diagonal. And one of the major challenges is, so although this is coming from an ergodic theorem, so it doesn't tell us what the limit is. And it's not an integrable model. So it's not one where we can, like there's no calculation, no like conjectured formula for what this value is either. So that sort of really limits we can work with. So in terms of what I mean by it, it's not an integrable model. Integrable models are, we've heard several talks of Alexei and Konstantin and Amol about different sorts of integrable models where using sort of algebraic methods, representation theory or determinantal formulas, and this has been to calculate exact things in important probability models. And this has been a major theme in probability over the last 3 decades or so. And it's made major progress in random matrices and diamond models and particle systems. And yesterday we heard about the Tacit model, totally asymmetric simple exclusion process, which has a sort of alternative formulation as something that looks like first passage percolation, except it's last passage percolation, which means that rather than minimizing the sum of the weights over paths, you maximize the sum of the weights over paths, but over oriented paths, so paths that are only allowed to go up and to the right. And if you take the weights to be IID exponential random variables, then this is an exactly solvable system. I mean, because basically it's in one-to-one correlation with Tasso.
But there's no formal definition of integral, right? It could depend on who you find.
Yeah, no, so I mean, possibly, right, yeah, I guess it's sort of a bit like, what is a closed form solution of something? It's, you know, it's, and maybe when I say first passage percolation is an integrable, it's because we're not smart enough to do it. But as of our current knowledge, there's sort of no expressions that you would call sort of integrable. Okay, but in this sort of particular variant of last passage percolation, you can write, there's a nice formula for the sort of leading order term. The fluctuations are n to the 1/3 with the Tracy-Widom distribution. And if you view it as a growth process, it sort of is governed by sort of the KPZ universality class. And so you'd like to say, well, okay, we know this for this integral model. Can it be transferred to other ones? So this was very successful in random matrices, where, you know, people had results about the eigenvalues for GUE, and then found that when you change the distribution, under some assumptions, you had universality. But in last passage percolation and first passage percolation, all those sorts of questions are wide open. So if we change exponential to anything other than maybe geometric, we don't know any of these sort of results, and the results are much weaker. Okay, so, but people conjecture that these are the same sorts of behaviors occur for first passage percolation. So let me just say, be more specific. Well, one result that we do have, Cox and Durrett showed that there's a limit shape. So if you take what you can reach at time t and then divide that by t, this converges almost surely to some deterministic shape B star. But we don't know what that is, and we don't know even basic properties of it. So it's conjectured that under some mild assumptions on the field, it should be smooth and have positive bounded curvature. And actually the positive curvature is quite an important property. A lot of work has been done in this area under the sort of conditionally under the assumption that the limit shape has a positive curvature, but we don't know that for any random field in any direction. Another sort of conjecture is that the passage times should, like with the integrable model, scale like n to the 1/3 in 2 dimensions and have Tracy-Widom fluctuations. Another sort of question you can ask about is the transversal fluctuation. So how far does the optimal path sort of detour away from just the straight line path between A and B? And here the conjecture is that it grows like n to the 2/3. Okay, so in higher dimensions, these exponents are expected to be different. But it's believed that in any dimension 2 and higher, they satisfy a scaling relation, chi equals 2 psi minus 1. And this scaling relation comes from like quite a simple heuristic. It's imagine you see in the distance a highway that you can drive faster along, and that will save you time. But you've got to weigh up the time you'd save driving on the highway with how long it takes you to get to the highway and back. So if you had a transversal fluctuation of size h, this sort of detour would increase the Euclidean distance. You just do Pythagoras' theorem by about h squared over n, which in terms of exponents is n to the 2 psi minus 1. And if you equate this by sort of how much you might save by sort of finding some region with better passage times, that's sort of n to the, what you could hope for is n to the chi, the sort of typical passage time fluctuation. So if you equate the exponents, then you get this scaling relation. Now, I should say that even the existence of these exponents is not known, but I could sort of reformulate this as saying that the expected transversal fluctuation is of the same order as square root of n times the standard deviation. Okay, so Shurav had a very nice paper on the scaling relations where he proved them under sort of fairly strong assumptions about the existence of the exponents, and also that quantities were sort of had exponential concentration on that scale, essentially. More recently, Ken Alexander, in the sort of rotationally invariant versions of first passage percolation, showed this under, still conditionally, but under a sort of smaller set of assumptions. Okay, and so our work will also be in the rotationally invariant setting. So this is not the normal first passage percolation model, and I'll describe several variants that have rotational symmetry. So one would be to go into the continuum and build a sort of smooth, continuous, rotationally invariant field. You could do this by, say, taking white noise and convolving it with some smooth, compactly supported rotationally invariant function, then maybe taking some function of that to make it non-negative. And then rather than taking the minimum over paths of the sum of the weights, we'll take the minimum over continuous curves of the integral of the field. So this would give you one sort of definition of a model of first passage percolation. If you prefer more discrete things, you could take things based on Poisson processes. So you could take a random geometric graph where you connect each pair of vertices who are at distance at most L. And then if A and B are two vertices in the graph, you could look at that are, say, in the infinite component, you could look at the graph distance between them. So this is sort of another notion of first passage percolation. Or take Voronoi tessellation, where you take the cells according to which Poisson point they're closest to, and then between A and B, ask how many cells you need to pass through to get from A to B. Or another model people have studied is the Howard-Newman model. So all of these give rotationally invariant models that are sort of morally like first passage percolation, and our results will hold, at least our first set of results will hold for all four of these, and also a broader class. So essentially you sort of interpolate, so a path gamma will be sort of an interpolating sequence of the Poisson points, and you take their pairwise distances to the power of beta, and if beta is greater than 1, this sort of incentivizes you to take pairs that are kind of close together. So it gives you something proportional to the Euclidean distance between them. Okay. So the first set of results are that in 2 dimensions, if we center the passage times and divide by the standard deviation, then they're concentrated in the sense of having at least sort of stretched exponential tails. Now, if I replace standard deviation with, say, square root n here, this would be fairly easy to prove by, like, certainly work of Keston in the 90s. The challenge here is that we don't know what the standard deviation is, so it's normalized with respect to, but we can still get concentration on that scale. You could also replace the expectation centering with n times mu, because what's called the non-random fluctuations, the difference between the expected passage time and mu times n, we also show is of the same order as the standard deviation. And finally, we show this sort of formulation of the scaling relations, that the expected transversal fluctuation is of the same order as square root of n times the standard deviation. So this, and we can only do this in 2 dimensions for reasons that I'll describe as we go on. Okay, So part of the challenge here is that we don't know what the standard deviation is, and as Yuval pointed out, one of the challenges is to get better upper bounds on that. So the sort of a simple upper bound is sort of basically of order root n, but the real thing should be n to the 1/3. What is, oh, sorry, yes. Theta is just going to be some small constant. You should think of theta as being like 1/100 or something. I would expect that, but we definitely did not prove that. Yeah. But for our purposes, so this kind of concentration is enough for all of the sort of many union bounds that we need to take. Okay. So in order to prove better upper bounds, we use sort of a approach which Schramm wrote a very nice monograph about, relating two terms that he described as chaos and superconcentration. And he gives sort of a very general framework for this, but I'm going to just give the definitions that are specified to the setting of first passage percolation. And actually, I'll just do it in the case of the vanilla version rather than the rotationally invariant one. So chaos will be saying that, suppose gamma is the optimal path, and then we take our field, and for on each edge with probability t, we resample the field or the weight on that edge with a new independent weight. So, and then gamma t will be the optimal path in this new sort of partially correlated field. So we'll say the path is chaotic if sort of for any value of t, the expected intersection of the old optimal path and the new one is sort of little o of n. So, so mostly they don't overlap. Superconcentration will be saying that the random variable, in this case the passage time, is more concentrated than sort of a baseline value. And in this case, the baseline will be essentially what you get from the Efron-Stein inequality. So an upper bound on the variance is just the sum over all edges of the expected square of the change when you resample edge E. Okay. And if you do this for first passage percolation, you get essentially the sum of the probabilities that edge E is on the optimal path, which is just like a constant times the expected length of the path. So this will give you something like order n. Superconcentration would be that if the variance was more concentrated than what you get out of the Efron-Stein inequality. And Schramm showed that in the case of Gaussian processes where the resampling is a bit different, it's the Ornstein-Uhlenbeck semigroup, then you get some equivalence between superconcentration and chaos. Okay, so in our case, you can also see this by writing down the variance in terms of the Doob martingale, where you sort of reveal the edges one by one in a random order, and then take the sum of the variance of the increments of that martingale. And then if you sort of play around with this, you get essentially an integral of the sum of the edges of the probability that the edge is both in the old optimal path and the new one, or equivalently just the integral of the expected value of this overlap over t. Okay, so I'll come back to this, but okay, so the Efron-Stein inequality said that the variance would be bounded by order n. As Yuval mentioned, there's a beautiful result of Benjamini, Kalai, and Schramm that says that in the case where the weights are Boolean, it's the variance is bounded by n over log n. Yeah, if you haven't read this paper, it's very short, and I really recommend it. It's a really lovely result. It was extended by Dameron, Hans, and Soso to a sort of wider range of distributions with the same n over log n bound. Oh, and I should say that the proof was using an application of an inequality of Talleyrand using sort of the hypercontractivity of Boolean variables. And Schramm showed or gave an example of something, maybe not exactly first passage percolation, but sort of like maybe a directed version of it with Gaussian weights, where essentially this n over log n was sort of the right bound. And so sort of what that says is that without using something more about the graph structure, then you can't do better than this. So we have to use something about the lattice in order to prove a n over log n. So what? Okay. Okay. Maybe. Yeah, I haven't thought about that. Okay, so what sort of properties can you say about the lattice? Well, one is that it's sort of self-similar in the sense that it looks like a grid of boxes regardless of how much you zoom out. So this suggests maybe a multi-scale approach to the problem. And we were able to implement this in sort of in the sort of continuous version of the rotationally invariant model, and show that for some very small epsilon, that the variance is at most order n to the 1 minus epsilon.
Not just the structure of the lattice, but also the individual nodes.
Yeah, yeah, I guess you know, everything looks like a nail when you have a hammer. Yeah. Okay, so yeah, so for the rest of the talk, I'm going to tell you about the proof. So at least try and give an impressionistic picture of that. So as I said, it will be multi-scale. So we'll be comparing sort of what's happening on longer length scales to slightly shorter ones. And so for the rest of the talk, you should think of n as being something going to infinity, and m as being like a very large constant. And so we want to compare sort of passage times of length m times n with passage times of length n. So we could do this by just dividing the plane into columns of width n. Now the passage times are, yes? Yeah, and then we immediately put a grid on it. Yeah. Oh, okay, I'll comment on this in a moment. Yeah, so okay, so the passage times across the columns aren't exactly independent, but actually they're very close to being independent. The more difficult thing is that you know, we don't know where it's going to intersect with these sort of intermediate vertical lines, but we'll sort of coarse-grain things and think of it as a series of you know, crossings of rectangles and parallelograms. And so in terms of where the rotational symmetry is going to help is that we'll be able to sort of give a comparison of what it's like crossing sort of a parallelogram like this versus crossing sort of a rectangle. And so we can sort of understand that the extra, you know, when these slopes are steeper, there's sort of a cost in Euclidean distance to that, and you'll get a sort of corresponding increase in the passage time. And if it's not rotationally invariant, it's much harder to say something about, something like that. Okay. So you could ask what the right spacing to take here between the horizontal lines, and the natural thing to suggest is, you know, what's given, the value given by the scaling relations, how much you expect the path to wiggle within distance n. But a problem with this is that we don't know that the standard deviation is in any way well behaved. It could be, you know, we don't know that, for instance, that it's monotone, or even that it's not kind of wildly fluctuating, which is maybe a problem for this kind of inductive argument. So we'll use a sort of slightly different quantity for this. Okay, so remember one of the results we want to prove is that xn centered around its mean has stretched exponential tails when you divide by the standard deviation. I'll just define qn hat as the smallest thing that you could divide by to give you the stretched exponential tails. This also might not be well behaved, but I'm going to kind of force it to be monotone by taking qn to be the maximum of qm hat times n over m to the alpha. And so this sort of forces it to grow at least like a n to the alpha. Okay. I should say qn hat is also an upper bound on the standard deviation. Ultimately, we're going to prove a matching, the reverse inequality, that up to constants, qn is less than or equal to a constant times the standard deviation. So, but that will come sort of like about 100 pages after this definition. So instead, we'll just do everything in terms of this quantity qn, and at the end of the day, say that this is related to the standard deviation. And then, because we want to sort of understand break paths up into a series of crossings of these rectangles and parallelograms, we'll need to be interested in not just sort of point-to-point passage times, but also sort of side-to-side ones. So where we take a rectangle, and I want sort of the minimum passage time from the left side to the right, and also the maximum passage time from the left side to the right over all starting and ending points. And I'll call this yn minus and yn plus. And the height of the rectangle will take according to, again, informed by the scaling relations of the square root of n times qn. And the goal will be of the first part of the paper is to basically show that these behave have satisfy the same kind of bounds as xn, just the point-to-point passage time. So so when they're centered, they have the same kind of stretched exponential tails. And the difference in their means from n times mu is also of order qn. Okay, so rather than prove this for you, I'm just going to show pictures from the paper. Essentially, there's sort of various kind of geometric arguments comparing side-to-side passage times with slightly longer point-to-point ones, comparing passage times across rectangles with passage times across parallelograms, and sort of thereby getting sort of extra distance associated with a parallelogram, and then using this to sort of understand how much sort of fluctuations you could have in this coarse-grained path. And essentially, we get a contradiction saying that if the non-random fluctuations were too big, if the expected passage time was more than a big constant times qn bigger than n times mu, then you would get a contradiction to mu being the law of large numbers, right? Anyway, so I don't want to go over this part of the proof, but in more detail. But once you have these sorts of estimates, you can readily get sort of at least the more difficult upper bound on the transversal fluctuations. And so this is by a chaining estimate. And so chaining, if you remember from when you first learned about Brownian motion, is sort of like the argument for showing that it's continuous. It's sort of breaking things up into smaller and smaller dyadic scales. And so if there's a transversal fluctuation that's a large constant times this wn, then we'll be able to find some dyadic scale on which the path essentially takes a big detour, a big kink. And if I draw this as sort of 3 crossings of parallelograms, the only way that the optimal path would choose to take this big detour is if the passage time across one of these 3 parallelograms was either much bigger than normal or much smaller than normal. And because we have estimates on the probabilities of those, we can show that such a scenario is unlikely and take union bounds and ultimately show that you're unlikely to have a transversal fluctuations on a scale bigger than this. And so now if we knew that Qn was also of the same order of the standard deviation, this would at least give us one side of the scaling relations, the more difficult side. It also, because we know that Qn is at most square root of n, it will also tell us that the path fluctuates by at most about n to the 3/4. So it's not, so these fluctuations are not sort of linear in size. And that will also be useful in a bit later. Okay. So the next part is trying to show that Qn actually is of the same order as the standard deviation. And to do this, we sort of inductively prove a better concentration bound. So Ramon was asking, what theta is, and basically it was just some small number. And now we'll replace it by some slightly bigger small number, which looks like we're doing nothing really, but with maybe a 1 over r extra factor in the exponent. So what is the point of doing that? It's the way in which we chose Qn. So suppose when n to the minus alpha Qn hat hits a sort of new running maximum value, then Qn will be the same as Qn hat. And then essentially the definition of Qn hat was, okay, if we take the centered random variable, normalize it by Qn, and look at the distribution of the tails, then the definition of Qn hat says that it's bounded above by this 2e to the minus x to the theta function. And we chose it in such a way that these meet at some point. Okay. Now suppose we also knew the improved, the better bound, then we'd say that the blue curve is also less than this x to the 4 over 3 theta bound. And when x is bigger than r cubed, this is smaller. So it means that this intersection point has to happen before r cubed. And the consequence of that is that, and also it can't happen for too small a value of x either. So it means that for some value of delta, the probability of having a deviation of delta times Qn is at least delta. And therefore the standard deviation is at least a constant times Qn. So at least for these record points, then this would be saying that Qn really is the same as the standard deviation. Okay, so, and then in order to prove this improved concentration, well, we only need to prove it for sort of x that are bigger than r cubed, where this new bound is better than the old one. And that turns out to be sort of quite easy to do because, well, okay, no, sorry. That, I shouldn't say that. I mean, we can, so why is it true? Well, you can think of the passage time as being sort of a sum over these passage times across parallelograms. Now, the central limit theorem has the effect that, let's say if you took random variables with a stretched exponential tail, added them up, divided by root n, then you get something closer to a Gaussian distribution. So this sort of adding up and averaging has the property that the tails of the distribution are getting better. Here you get a similar kind of thing, but it's a bit more complicated because we also have to do the optimization over all the possible coarse grainings. And it doesn't work in the bulk, it doesn't tell you much in the bulk of the distribution, but when you're out in the tails of the distribution, you get you get an improvement in the tails. And really this is a consequence of saying that neither theta nor 4 over 3 theta was the right thing to put at all. As Ramon said, we should have like 3 over 2 there. Okay, but so as a consequence, we know that when we're at one of these record points, then Qn sort of matches the standard deviation.
This transfer from theta to 4 theta is only possible
That's why we took a fairly small value of theta. I mean, we didn't work on what sort of was the best kind of value of theta that we would need, partly because we didn't need that. Okay, and so in order to show that we keep sort of hitting sort of new record values for Qn, we need to show that essentially the variance keeps growing. And in 2 dimensions, for first passage percolation, and this is really the part where we need 2 dimensions. Everything I've said so far would have worked fine up in higher dimensions as well. But the Newman-Pisa argument we use for lower bounds on the variance is really a 2-dimensional property. And it's about sort of saying, how much variance do you get from each individual edge? So to make it easier to describe, I'll talk about the original version of first passage percolation. But suppose you take an edge and it's on the optimal path, and maybe it's 5, and then you resample it and it becomes 3 instead, then the passage time will have decreased by 2. So what this sort of says is that if you look at the difference in the expectation and the expectation given the value at edge E, you can get a lower bound on that, or the square of that, as essentially something of order the probability that E is on the optimal path squared. And so as an overall lower bound, you'll get something of the order of the sum over the, or this should have been edges, the probability E is on the optimal path squared. Remember the Efron-Stein bound was sort of the other way around, but without the square. And now if you know the path is confined to an n by n to the 3/4 box, then you would sort of, like the smallest this could be is if it was just a uniform probability, and then you would get n to the 1/4. So this gives a lower bound of n to the 1/4 for the passage time. So it's sort of, so the variance is tending to infinity, like n to the 1/4. This was from the transversal fluctuation bounds, because we said that the transversal fluctuations were at most square root of n Qn, and Qn was at most root n, so you get n to the 3/4 from that. So with high probability, it's sort of in a strip of maybe n to the 3/4 plus a little bit. Okay, so we want to do something similar like this, except to show that a sort of more local version of it, to show that when you go from something of variance, compare the variance of length m to m times n, and show that it increases by m to the 1/4. And so we'll do this rather than resampling one edge at a time. We'll resample a block in the field that's n by wn at a time. But the challenge is that it's harder. If you resample an edge and you get a smaller weight, then the passage times can only decrease. But if you resample a whole block, it's harder to tell if the overall passage time increases or decreases, because the path might go through it from left to right, maybe it goes from top to bottom, or left to top, or it enters several times. And we sort of have to average over all the possible exteriors of the block, and maybe they cancel out in some complicated way. So we deal with this by sort of saying that actually we'll define some event in some that holds for most places along the optimal path in a local neighborhood around the box, such that if when you resample this particular block, the left to right passage time decreases a lot, then the conditional expectation of the passage time will decrease a lot. And in doing so, you can sort of prove this, that the variance is growing like this. This will say that you get that Qn hits sort of record points that are sort of regularly, and sort of essentially every window between n and m times n will have at least one point where Qn and the standard deviation are of the same order, and then it's not hard to sort of extend that to all values of n. Okay, So that's enough to prove, so all those ingredients are enough to prove the scaling relations. And then what's left is to sort of then prove the chaotic behavior, and from that get a better upper bound on the variance. So we go back to this sort of martingale decomposition, and so if we wanted to, so the trivial upper bound on the variance is n, and you can see this from this sort of decomposition, because if you look at the expected intersection between gamma and the resampled one, gamma t, this is a decreasing function of t. And when t equals 0, this is of order n. So, and so essentially that's the Efron-Stein bound, and you get a constant times n. But now if we want, suppose we want to get an improvement and get this to be n to the 1 minus epsilon. This would have to decrease really quickly. So it would have to become very chaotic even after adding just a very small amount of noise. So you'd have to resample an n to the minus epsilon fraction of the edges and already have an expected intersection, sorry, this sum shouldn't have been there, of n to the 1 minus epsilon. And that's something that we don't really know how to do, at least directly, very well. Showing that just a sort of very, very light amount of resampling already makes it chaotic. So this would be sort of quite a challenging quantitative statement to prove. Yeah, sorry, I said that shouldn't have been there. Yeah. Okay, so so instead we're going to do a multi-scale version of this sort of chaos argument. And instead of resampling an edge at a time, we'll resample a block at a time. And then we'll get an upper bound on the variance of paths of length m times n as constant times the variance of length n times an integral of essentially the expected number of blocks, both gamma and the resampled gamma intersect. Okay, so this looks very similar to the previous slide, which I said was hard. So why is this better? Well, suppose we can show the most sort of modest version of chaos you could imagine. So essentially that, so when t equals 0, this is just the number of paths that the gamma intersects, which will be order m. Now I want to say that the larger values of t, this is sort of little o of m. So just the sort of most basic unquantitative version of chaos you could ask for. If we can establish that, then we can show that the variance of lengths xmn is at most m over 2 times the variance of xn, and that will imply that it's growing at an like n to the 1 minus epsilon rate, where epsilon is log base m of 2. For some embarrassingly small value of epsilon that we never calculate. So this is the plan, and so essentially we just need to show that on this in this multi-scaled sense, the path is a bit chaotic.
Someone went from little o to 1 half.
Yeah, well, I mean, okay, so there was a constant here, so I just need this to be smaller than like m over 2c. Yeah. So we.
You don't know that constant.
Yeah. That's right. But you're right that, you know, even like a small constant times m here suffices for this. But we will actually be able to show this. Okay. So in the time remaining, I'll give you a sort of sketch of how we show that it is chaotic. So imagine that the optimal path goes through this blue block here. And then we do some resampling. And then this sort of green block here suddenly has a much better path going through it. So maybe the optimal path will choose to go through that one. But maybe the path does something more complicated. Maybe it sort of goes through both the blue one and the green one and sort of wiggles around a lot. So we need sort of a more complicated sort of set of events to ensure that if those events happen, then locally the path won't go where it used to go. So we asked that, first of all, there's a green block where the passage time near the optimal path, where the passage time gets a lot shorter, but also that there are sort of barriers, where these red shaded regions, where essentially any path that goes from one side of these barriers to the other will have a much bigger passage time than typical. And in the sort of unshaded regions in between, we'll sort of ask that the passage times are roughly typical. Okay, so, and I won't give you the full definitions because it's like several pages of LaTeX, but essentially if you set this up in the right way, you can say that, well, after resampling, either the new optimal path sort of goes through this green one and avoids the blue one, or maybe it goes somewhere completely different. But in either case, it doesn't go through the blue block. And so we have sort of a separation from where the old one was to where the new one was. And our goal will be to show that these sort of separation events happen at a sort of constant density of sites along the optimal path. And there's a couple of challenges of this. One is that the environment along the optimal path is kind of special by virtue of it being the optimal path. So we use sort of two main tools for this. One is a kind of percolation event to show that things behave in a fairly typical way along most of the optimal path. It's very unlikely to have any path that's not too wiggly that has weird environments most of the way along. And then for the barriers, these are sort of increasing events, and we use the FKG inequality to establish those. And actually, this is the reason why this, for this final part of the proof, the new upper bound on the variance, that it only applies in the case of the continuum one, because that model we know has the FKG property, whereas not all of the discrete ones, like the Voronoi tessellation one, doesn't obviously have the FKG property, for instance. I think for the for the random geometric graph one and the Howard-Newman model, we can probably do it. The only issue there is sort of, we've done all this in a general setup where we've defined sort of passage times for any point in the plane. And that includes points that are not one of the Poisson points. We've sort of like tried to shoehorn a sort of discrete model into a continuous setup. So there's some issues about how you define sort of the beginning and end of paths. And those sort of might mess up the FKG property, but that should only affect things by something of sort of like an order 1 scale of things. So, so probably with some extra work we can do those, but we didn't. So we ultimately show we have these separation events at a sort of delta fraction of sites along the optimal path. But delta will be quite small. And so that's saying that, they only overlap on a 1 minus delta fraction of the optimal path, which is not very chaotic yet. So we want to improve this. And so, as Yuval pointed out, we like multi-scale arguments. So we'll throw in another layer of multi-scale between n and m. And so choose sort of L intermediate scales, and then try and find these separation events on sort of smaller scales and medium ones and bigger ones. And overall get the fraction where they're not separated is at most 1 minus delta to the L. And then the idea is that if m is big enough, we can choose L big enough to make this sort of small enough to get the improved bound on the variance and complete the induction. Yeah, and that's it. Thanks for listening.
for the rotationally invariant, do you actually trying to use the curvature assumption of the shape function?
Yeah, so we, the place where we use the rotationally invariant part of it is essentially in the very first part of the proof, where we're, oh, that's not good. Oh, maybe I should go back into, okay. Sorry about this. Okay, this part where we're essentially like, here we want to compare sort of passage times across a rectangle with passage times across a parallelogram. And sort of there I've sort of rotated the rectangle. And you can't do that so there we really need rotational invariance rather than just curvature of the limit shape.
How much are you rotating? Because it's not 45 degrees.
Right, yeah, no, I mean a fairly modest amount, that's true.
So it looks like if there's smoothness, then
yeah.
should be very close.
Yeah, so I think, I don't know about the scaling relations. Well, okay, and I guess another thing that's useful is also, like, we don't necessarily know that the variance is the same in every direction. So it's very useful for us to know that those are the same whatever direction you go in.
But it's possible to take somehow looking at the maximal variance.
Yeah, so I think
More hard work.
no, I think it might be the part of the proof about the improved variance bounds. I think there it might be possible to sort of say something just assuming curvature, but that will be a lot uglier than an already sort of quite technical paper. But yeah. So it's I mean, for the methods that we've used so far, we really do need the extra benefit of rotational invariance. Okay. I might say one more thing. We're not writing it down at the moment, but the upper bound on the variances ought to work in any dimension 2 and higher, because the issue with the reason why we needed the two-dimensional assumption in the scaling relations part was essentially to show that the variance kept growing. But if your goal is to show that the variance doesn't grow too much, then you don't have to, then if it's not growing at all, then you're already very happy.
But in 3 and higher, isn't the conjecture that in fact it's not growing?
I think it's still growing in 3 dimensions, and then I've heard different things about higher dimensions, depending on who you ask.
Any other comments or questions?
I have a very quick question about the behavior lecture.
Okay.
We have a specific configuration of the first best percolation on Z2 or higher dimension, and does it have a good algorithm to find the optimal pace between two very far points?
I mean, I guess this pathfinding is kind of a classic computer science question that your, I don't know, real-time, Dijkstra, like your real-time strategy game implements when in computer games, and it's so that's I guess something maybe going back to the 60s or so, or
But because of the structure here, you might be able to do it faster.
That's maybe.
You don't have to explore all possible paths.
Yeah, I'm not sure that we could. I mean, certainly we only need to really look at this sort of n by n to the 3/4 box, but I don't know that we can sort of dispense with looking at most of that, but yeah, maybe.
The path is not going to go
Sure.
that path.
Sure, but until the end, until very close to the end, you don't really know where the path is going to be. So you probably have to keep revealing a lot of stuff in order to. I mean, in a sense, so the chaos argument would say that if you just reveal them in a random order, you only work out sort of the approximate trajectory of the path very late. So you don't save much time, but maybe there's a smarter way of exploring it.
So let's thank Allan for what